So I should be visible now. Can you all see the screen? Can you all see the PPTs?
Yes, sir.
Okay. So today's lab will be on code converters. So we have already seen the various codes. Today we are going to implement the code converter circuits uh, after looking at how exactly to design it. So this is also a small part of the combinational circuit design, and this is what is you should know. It will also give you more practice on K-map, but today I'll go through K-maps. Whenever I'm solving something, I'll go through K-map a little bit faster than before. So I want to just see whether you are able to solve it faster or not. If not, then probably I'll again change my strategy of dealing with it. So let's start today. That is the topic for the day is combinational circuits, and of course my teaching pattern is that every circuit will be followed by some kind of simulation, which is basically our lab kind of thing. So we will slightly mix it and go ahead. So for today's lab, uh, the agenda is going to be dealing with combinational circuits and then finally designing them on DSCH or even Logisim, whichever is compatible, you can just do that. Now, what is combinational circuits? So what is the meaning of the name combinational? So combinational means that it's a combination of many gates. It may be AND gates or it may be OR gate, it may be anything. So a combination of all these gates put together in a certain fashion can be used to develop some kind of logic. So for that, we generally use combinational circuits. Now let's see what these combinational circuits are. A combinational circuit is implemented using logic gates. Very important. That is, it is using logic gates. Something to note here that combinational circuits do not use memory elements like flip-flop. So when the moment you use flip-flops, we say that the circuit is now sequential. It is not combination. So we'll see that slightly in the later part of the course. So here, very important, combinational circuits are basically implemented using logic gates, and the output is determined directly from the combination of the input applied to the circuit. That is the meaning of this is like, let us say if the number of inputs are 4, let's say ABCD, then you can straight away write a function of ABCD in terms of A, B, and C. So just this is just for example, you can just write a function directly in terms of A, B, and C. Normally, combinational circuits are used to implement Boolean logic functions. So, like I said here, that this will generally be used to implement logic functions. The combination of logic gates accept the input signals in the form of binary signals and generate the output signals based on the logic functions which are used to implement it. So it should be noted that both input and output are in binary form. So binary means now onwards it is obvious that our input is also digital and output is also digital. So what we are actually doing is we are creating a black box. What we are going to do is we are going to design this combinational circuit using gates by looking at how many inputs are expected. So these are n number of inputs, and then we will finally decide based on these n number of inputs how many outputs are there. For example, the inputs can be A, B, C, D, but we can have F1 of A, B, C, D. We can have F2 of A, B, C, D. We can have Fm of A, B, C. So that is possible, where here n is equal to 4. Like if n is equal to 5, A, B, C, D, E, then we can have F1 to Fm of A, B, C, D, and E. So in a combinational circuit, we can expect multiple inputs and multiple outputs. Sometimes on the same input, multiple outputs can be dependent. So now, what is the strategy to design this combinational circuits? So if how the specifications are given to you, and then how you can actually arrive at a logic circuit, that is going to be the experiment for today. So I will suggest that each one of you should write these steps as I explain them. At the same time, listen to what I am saying. First, state the problem. Step number 1 is state the problem. State the problem means what? You have to look for the Boolean function. You have to look for the Boolean function. After looking at the Boolean function, you should count the number of inputs and outputs. For example, whether there are two Boolean functions, f1, f2, which are in terms of a, b, c, again, which are functions of a, b, c. So there can be two functions and there can be three inputs. So A, B, C are the three inputs and the two outputs are F1 and F2. A, B, C are the inputs and outputs are F1 and F2. Or there can be infinite or number of outputs based on A, B and C. It will not be actually infinite is not the right word, but there can be many outputs based on A, B and C. So count the number of inputs and outputs available. That is our step number 2. Assign a symbol or letter for each input. So generally in the Boolean function, if ABC is given, don't break your own head and make it XYZ. Let it be ABC only for each input and output. Obtain the truth table which defines the problem stated with the conditions by input and output variables. So this is the place, point number 4 is the place where we actually start applying some logic on the given data. Obtain the truth table. Once we get truth table, immediately we can convert that truth table into a Boolean function. So sometimes the Boolean function only will be directly given to us, or they may give us a function of a, b, c, and they may write summation m 1, 2, 3, 5, 7. So explicitly terms are not given, but the min terms are given. So when this is given, the Boolean function may be very big, but to reduce the number of gates, so this step number 5 talks about reduction. When you talk about reduction means you are talking about optimization. The same input, you can get it with lesser number of gates. And what are the options that we have studied? We have Boolean algebra, we have K-map, and though this is not there for you, Quine-McCluskey, but still I have included that in my notes, so you can also simplify using Quine-McCluskey. But our focus will be completely on K-map. So if you are using K-map, you don't have to think about anything else. Everything will be pretty straightforward. So just to minimize that, we will always go for K-map instead of Boolean algebra or Quine-McCluskey. But the options are with you. If you are comfortable or very good with Boolean algebra, fine, you can go with that also. But we have already seen the limitations where Boolean algebra can become too much to solve for. Step number 6, draw the logic diagram for the combination of the given input and output variables using logic gates. So in the experiment, generally you have to write the procedure. So this is the procedure to design any combinational given circuit. So I hope you all have written this. If you have, Karthik, have you all written these points down?
No, sir.
Okay, so once you write all the points down, just write a done in the chat box so that we can go ahead. Read the statements again and again so that it sinks into you. First is state the problem. So state the problem can also be like this, something like this. They can say there are three sensors. One is temperature sensor, one is distance sensor, and one is uh, maybe we can say a dust sensor. Okay. So these three inputs are coming. The three inputs are digital, which are being fed into a computer. Now the output should be one only if a certain combination of for a certain combination of this sensor. That means if you want to detect fire which is in very close proximity, then probably the temperature sensor should be high, then the distance sensor should also be high, and the dust sensor can be anything. So based on these combinations, so these three inputs can be your three combinations, and based on this you can design a digital logic using gates to deal with this situation. That is, you can decide for which combination of the inputs your output should be high. Now you can also imagine like this, that inputs are heat, distance, and probably smoke, because whenever there is a fire there is smoke. So there can be two or three operations that you need to do. You may have to sound the alarm, you may, so that is your one output. You may have to blink some lights, that can be some other output, and you may have to start the water sprinkler systems, that can be your third output. But the input is the same, that is heat, then your distance, and your basically your smoke detection. So these are your three inputs. So now based on this, can we actually design a combinational circuit? That is the question. So that is the agenda of today's lab. I hope you have understood this. If you have uh, completed writing this, just put done in the chat box. I cannot see any done till now. Anushka, can we go ahead? Yes. So can we go ahead? Can somebody unmute and say something?
Yes,
Yeah,
sir.
yes, sir.
So just write done in the chat box. Okay, I can see now. Maybe there is some delay. Sorry. Okay. Okay, let's go ahead. Just keep this page in the mind, because that's the steps that we are going to follow. Not very strictly, but yes, somewhat in the same order. Now, when you are designing something, some constraints that should be considered during the design, because the word is design. Design means it should be optimized, it should be high speed, it should consume low power, and it should take minimum space. So in order to look at all these four or cover these four constraints, we should, the first constraint is you should minimize the number of logic gates. So for this, we are actually using K-map technique. Then we want minimum number of input variables. That means we should see that even though there are 3 or 4 variables, are some of the variables redundant? So if we can get rid of them completely, whether that is possible or not, that also we should look for. Then least possible propagation delay through the path of the output. So this third number point is slightly valid when we do some adders. Less number of interconnections. So we don't want more number of wires. We want less wires. Wires, because what happens is, why we want less number of interconnections, because interconnections lead to 2 problems. One is delays. If the wire is longer, it will cause higher delay. If there are delays, it causes problems of synchronization. It causes a problem of synchronization. So sometimes I start dot at 2 o'clock, and if you join in at, let's say, 2:10, then there is a delay of 10 minutes. So initial 2-3 minutes or 5 minutes you have to again spend on synchronization. Means what's going on. So you need to spend some time on that, and that causes even more delays. That is the thing. And in modern day electronics, we have to deal with another problem called as crosstalk. We have to deal with crosstalk because if the wires are very closely spaced, then through some laws of electrostatics, I can prove that uh, the that the voltage on one line can go on the other line. That is, if you are sending a 1 on line number 1, by the time it reaches the output, you will not get anything on line number 1, but on line number 2, you will get that one. So that is called as crosstalk. Anyways, this crosstalk and delays are not a part of this particular course, but as you move ahead to VLSI, which will be based on digital logic design very heavily, these problems will be spoken about there. That's why your number of interconnections should be less. Let's say that these interconnections are carrying the clock signal, then it creates some more problems called as clock skew or clock jitters. So again, this interconnection should be as small as possible, and the longest interconnect in any modern day processor like Intel Core i3 or i5 kind of processor would be just 1 micron or less than that. So that's the longest length of the wire. So that's how interconnection. So I hope you understand the seriousness of these interconnects. Definable fan out or driving capability of each gate. So what is this fan out? Definable fan out means, let's say I have a NAND gate. This is a 2 input NAND gate. So this is the output of the NAND gate. So I want to know how many such NAND gates I can again connect of its own type. So if it's a 2 input, it's a 2 input here also. How many NAND gates I can connect like this of its own type at the output. Because we have already studied in BEE that here I will get some current I, and by KCL, if there is a node, then the current will divide at that node in some or the other way. So if this the incoming current is I, here I'll get I1, I2, I3, and I4. And Kirchhoff's current law says that at a node, the sum of incoming currents is equal to the outgoing currents. What it also means is, like, let's say if there is 10 milliamperes of current here, then I1 would be 2 milliamps, here it might be 3 milliamps, or here it might be again 2 milliamps and 3 milliamps. depending on this I1, I2, I3, I4 will depend on what is connected at the output. So that defines the fan out of the gate. So we should have minimum. So you cannot come up with a logic wherein logically everything is fine, but this fan out specification is not met. That is why mostly the all the gates are available up to 8 inputs. Beyond that, we don't have any gate. So that is one of the reasons. But okay, we will see this as we design something. So first thing is code converters. Now we have seen binary to gray, gray to binary, BCD to gray, BCD to binary, and whatever. So we will design a few code converters today. Code converter is a logic circuit that converts one type of binary code into another type. So you have understood, or we have already discussed how to convert, but now you want a circuit to do it. We already know the logic of conversion, but now you want that same operation should be done by a logical circuit. You doing it and logic circuit doing it is slightly different. So the focus is on the design of the logic circuit, which will do this code conversion. The binary codes that we shall implement in today's lab is BCD to binary coded decimal, then XS3 codes, and then we will deal with gray codes. So binary to BCD, XS3, and gray codes. Okay. First design step for code converter, somewhat similar. So we will just quickly go through this. Make a truth table to convert code from one to another. Draw the K map. Simplify the K map and obtain the Boolean expressions, and then implement the logic diagram. So you can just note down the points, make a truth table, draw the K map, simplify the K map, and implement the logic function. And these 4 points are the points that we have to follow in all kinds of design. So please note down design steps for code converters, only what I have underlined. Once you are done, just write done. Karthik, Anushka, and Kashmira, just while everybody is writing, are you able to all see the recordings?
Sir, I actually haven't tried it, but we'll let you know soon.
Yeah, so I just
Yes,
want to
sir,
know.
I can see the recording. Yes, it is
You
available.
okay? And there is one student from your class. I think his name is Abbas or something. So when I send you some documents on Teams, just forward it to him on WhatsApp because he is in Kashmir and there they have only 2G network, which
Zahir,
is, yeah, Zahir, or I don't know.
Zahir and Murtaza.
Ah, so they are facing that problem there. So, but WhatsApp connectivity is there. So let us just forward them these documents if possible. That is why I have also started sending you the documents on WhatsApp. So are you receiving them?
Yes, sir.
Okay, so just forward them to whoever is not connected to us. Okay, so let's go ahead. The first one, let us do the first one. Binary to BCD code converter. The first converter is binary to BCD code converter. So just start drawing this table. So the binary codes are A, B, C, and D. So we are just looking at 16 bits for now. So please note here what we are seeing at is binary to BCD. That means binary is the input and what we are expecting at the output is a BCD code. So A, B, C, D are my inputs and I have B4, B3, B2, B1, B0 as my outputs. You can now see the number of inputs are 4. A, B, C, and D are 4 inputs, and the number of outputs are 5. The number of inputs are 4, and the number of outputs are 5. So please note this thing. So this is the demarcation line between them. So this side is your input, and this side is your output. Now, you should note here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So this B4, this B4 is actually for determining whether it is valid or invalid BC. So you can look at this particular demarcation here. Till 9, 0 to 9 are valid BC. 0 to 9 are valid BC. But after 9, 10, if I want to represent 10, then 10 is actually 0001 followed by 0000. This is how I represent 10 in BCD. That is why you can see here that I have written here 1 and then again I start from 0, 1, 2, 3, 4 and 5. So you can see here 10 B4 indicates that it is not a valid BCD because it is 10, 11, 12, 13 like that. So that is what I have done here. So B4, so if you just look at this, B4 is 0 for valid BCD. B4 is 0, 0 for a valid BCD number. And B4 is equal to 1 for an invalid BCD number. So here you will start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you will make this bit 1, B4 as 1. And then again write 1, 2, 3, 4, 5, 6. So this kind of outputs are used later on in BCD adders. That is why we are first identifying that these are invalid BCDs and then using the same to add using BCD adder, which probably we'll do tomorrow. So I hope you have drawn this table. If you have drawn this truth table, just write truth table done. So I'm just removing the things for you. This is our initial table. If you have copied this truth table, just write truth table is done. 4 inputs, 5 outputs. Actually, 4 inputs should give me 4 outputs only, but we have added B4 to indicate valid or invalid BCD. Okay. So I'll wait for another 2 minutes, just in case somebody is still writing. Now, here you need to understand that B4 is a function of B4 will be a function of A, B, C, and D. B3 will be also a function of A, B, C, and D. B2, B1, and B0 likewise will also be a function of A, B, C, and D. So the 5 outputs are dependent on the same 4 inputs, that is A, B, C, and D. So 5 outputs are there, but they are dependent on the same inputs A, B, C, and D. That is why now we will look at one output at a time. We will try to find out what is B4 equal to in terms of A, B, C, D. What is B3 equal to in terms of A, B, C, D? What is B2 equal to in terms of A, B, C, D? And similarly, B1 and B0, what they are in terms of A, B, C, and D. So that is the objective. Once we get the Boolean function, we will be able to draw the logic diagram. Right. Step number 1. Step number 1. Calculation of Boolean function for B4. Calculation of Boolean function for B4. Now, I want you all to keep the truth table in the front when you are drawing the K-map. Your truth tables should be in the front when you are drawing the K-map. You
Sir,
can look.
sorry, sir. Can you please show the previous slide, please? I haven't completed. Sorry, sir.
This is just for explanation. You don't have to. Okay, in whatever way you want, you write it. But this is just for explanation. I'll wait for 2 minutes. Don't worry. If anybody has got any doubt in the truth table, please ask. Why one here only? Why not somewhere else? And like that. Vishwas, just let me know once you are done. Huh?
Okay, sir. 2 minutes, sir. 1 minute.
Yeah, yeah. And in the meantime, every one of you just keep your DSCH open. Open your DSCH. So just open it if you are done, but focus on how the designing is done.
Yes, sir.
So
Done. Thank you, sir.
first somebody told us design from convert from binary to BCD. So that is my problem statement. Then I did a truth table for that. So I just first wrote down what I am supposed to do in the form of truth table. There I identified how many inputs are there and how many outputs actually my system will have. So I decided there will be 4 inputs and 5 outputs. So this is your truth table. This is your K map just for your understanding. Now you can see in your truth tables, you can see that B4, that B4 is 1. What are we doing? B4. We are calculating the Boolean function for B4. B4 is 1, 10 onwards. That means 10, 11, 12, 13, 14 and 15. B4 is 1, 10 onwards, 10 and 10 onwards. That is 10, 11, 12, 13, 14 and 15. So in the 4 variable K map, why 4 variable? Because I have got 4 inputs. I get a K map like this. At 10, 11, 12, 13, 14 and 15, I will put the ones. So I will get a K map like this. Now I want you to tell me how many pairs, how many quads, and how many octaves. Type in the chat box. Yes, there is a slight delay, but yes, I'll wait for half a minute. Okay. So this is one quad that I can see, and I cannot see any octave because there are only 6 ones. And to make a octave, I should at least require 8 ones or right. So Tanvi has given the right answer. Yash, there are 2 chords. Atharva, there is no pair. Vishwas, there are 2 chords. There are 2 chords. All of you can see it. Yes, Shubham, you are right. 2 4 cells with overlap. Prathamesh is also perfect. Sanmesh, 2 chords. Are you getting these 2 chords, Sanmesh?
Yes, sir.
Okay. Yeah. So Gaurav, Hemant, Vishwas, are you convinced that there are only 2 chords and no pairs?
Yes,
Yes,
sir.
sir. Sir.
Okay. So now what
Yes.
will be the terms? So we will get 2 terms. What will be that? Now this is a quad, so it can eliminate 2 variables out of A, B, C and D. So you should get only 2 variables corresponding to each quad. What are they? Yes, Tanvi is also right. AC plus AB. Divya is the first one to give that answer. So let's see. So the first one is A and C or AB, and the other one is AC. That's right. So good. AC and AB. So B4 you can write B4 is equal to AB plus AC. B4 is equal to AB plus AC. B4 is equal to AB plus AC. Okay, great. So out of the 4 outputs, now out of the 5 outputs, I wrote one of the outputs in terms of the given inputs. Now similarly, if you look at B3, next you write calculation of Boolean function for B3. Calculation of Boolean function for B3. So the K-map for reference is there on your screen. So wherever there is a 1, at that particular position, you will write a 1. If there is a 1 for maybe 15 or 16 or whatever, just fill the K-map and tell me how many quads and how many pairs. So I'll give you 2 minutes for that.
Sir, can you please repeat because I didn't get that how to select those. Yes, sir. Here 12, 13, 14, 15, 11, 10.
Okay, so go to the truth table.
Okay, yes, sir.
Go to the truth table and see column of B4. See column of B4.
Okay. Yes, sir.
So for 1010, for the input ABCD 1010, B4 is 1.
Yes, sir.
For
10.
1010 ABCD, B4 is 1. Then
Yes.
again, B4 is 1 for 1011. Then
Yes.
1100, 1101, 1110, and then 1111, which is
Okay.
precisely 10, 11, 12, 13, 14, and 15.
15. Okay, okay. Like for B3, it would be 8, 9, 8 and 9 only.
Yeah.
Okay, okay. Thank you, sir. Got it.
So please ask the doubts because it will solve others' doubts also. So you are not just asking it for yourself, but you are also clearing the doubts of many others. Okay, so I'll go to B3. So you can see only for 8 and 9, B3 is 1. In all other places, in all other places, B3 is 0. Can you observe that? So here you will get just one pair. So who is the first one to give the answer? Let's see. Divya has given it A bar, B bar, and C bar. That's right. A bar, B bar, and C bar. B3 is one pair. Yes, Sanmesh, you are right. Prathamesh Satam, sorry. Smita, A, B bar, right. Yes. Hemant, Omkar, Atharu also has given the right answer. So simple. B3 is A, B bar, and C bar. Now, can you tell me for B2, B1, and B0? So B2, B1, and B0 can be little complex. So let's go to B2. Let's go to B2. So again the K map for reference. Now you can see B2 is 1 for a combination of 0, 1, 0, 0. Look at the truth table. Then 0, 1, 0, 1. Then 0, 1, 1, 0. Then you have 0, 1, 1, 1, 1. That is 7. And then directly it is for 1, 1, 1, 0 and 1, 1, 1, 1. So B2 is 1 for which combination? That you tell me first. B2 is 1 for which combination? Type in the chat box. B2 is 1 for 4, 5, 6, 7, and then 14 and 15. 4, 5, 6, 7, and then 14 and 15. So 4, 5, 6, 7, and then 14 and 15. In these positions, you will now write ones. Correct. And Deepak, you have to add 14 and 15 also to it. Deepak, can you unmute and talk?
Yes, sir.
Deepak, for 14 and 15 also, you can see B2 is 1.
Yes, sir.
Yeah. So now this is one quad. This is another quad. So you have A bar B and this is going to be BC. Just check it. A bar B and BC, right? Divya is right. Perfect. So I have been recording the performance of this class and let me disclose it that it is my conclusion that Shubham, Dalvi and Divya are the highest performance till date. There are others also in line, but the first two are Shubham Dalvi and Divya Jain. So good and keep this performance throughout the semester. Great. Okay. So B2 will be A bar B plus BC. Now similarly, I want you to do for B1. So let's go for B1. So now for B1, you can see B1 is 1 for 0010. So this is 00 and 10 is this. So that is 2. Then we have 0011 is 3. Then we have 0110 means 6 and then 7, 6, 7. Then we have just check it. Then we have 12 and 13. So that's where you got. So this is one pair and this is one quad. So obviously this will be A, B, C bar and this will be A bar, C, A, B, C bar and A bar, C. Yes, Amit, you are right. 2, 3, 6, 7, 12 and 13. Perfect. Now do the K map from that, Amit. Atharva, yes, your answer is right. Even Yash, Prathamesh, yes. Prathamesh, it's not B3, it's B1. Prathamesh, can you unmute and confirm that?
Yes, sir. Yes, sir. It is a typing mistake. Sorry.
Okay, yeah, it's B1. Okay, Shubham, Deepak, perfect. Okay, great. So that's my B1 will be A, B, C bar plus A, C bar. A bar C, sorry. Okay, and now just tell me the answer for B0. Tell me the answer for B0. B0 is the simplest. So tell me the answer. Divya, no. For B0, it's not C bar D. It's not C bar D. Check it again. Yes. Tanish has given the correct answer. That is, it is just D. It is just D. That means this output depends only on directly on the input. It doesn't even require a gate. It does not even require a gate. So let me just show you the calculation of B0. the min terms are, so your K map should be like this. So it's 1, 3, 5, 7, 9, 11, 13, 15. Because there are alternate ones and zeros. And obviously now you can see that it's a quad. You will get a quad here. So that quad will give me, so this A and B will completely go. And out of C and D also, what is not changing is D. And hence the answer is D. Good. Perfect. So Tanish, Deepak, Pratik, Hemant and Asmita have till now given the right answer. So to summarize, we have got 5 inputs B0, B1, B2, B3 and B4, and all are in terms of A, B, C and D. They are not just a functions of A, B, C and D. They are reduced functions of A, B, C and D because we have already used K-map reduction technique on the given truth table. So with truth table, we filled the K-map. By K-map, we reduced the equations. And with the reduced equations, now the next step will be implementation of the logic function. Will be the implementation of the logic function. So B0 is equal to D. Perfect. I can see many Karthik, Tanvi, yes, Harsh, Ashish, Smita. Okay, great. So now go to DSCH. Go to DSCH. Open DSCH. Once you open DSCH, just type DSCH. Open DSCH. Yes, Karthik, all of you have opened DSCH.
Yes, sir, it's opening.
Okay. Okay. Now in the DSCH, you can see the palette. You can see the palette. In the palette, you can see these push buttons A, B, C, and D. So you can see this. First, take 4 buttons A, B, C, and D. So here, if you are getting A, I want A bar also. If you are getting B, I want B bar also because my logic functions have got both A and A bar, B and B bar, C and C bar, D and D bar. So I generate A, B, C, and D, and I also generate complements of them A, B, C, and D bar. So I'm just stopping the presentation. Yeah. So I'm going to DACH. Yeah. Karthik, can you see my screen of just
Yes,
doing a
sir.
count?
I can see it.
So open DSCH. You should be able to see this black screen. Now you pick up this button. You just drag and drop this button. Just drag it. You will get. You can see that this pin, once you drag and drop, it is rightwards. The input is rightwards. But I told you that I want this thing to be. I want it to be facing down like this. I want to draw a line down. So what I'll do is, you can see an option here. You can see an option here, rotate to right. Click on that option and then click on the button. Click on that option, rotate right, and then click on the button. So you can get this I in 1 facing downwards. You can get this I in 1 facing downwards. You can make this small. You can make this small as possible so that you can fit. We have to fit 5 functions. So this thing you can just make it small by using zoom in or zoom out. So we can just make it small as possible, and you can use these buttons here. So you can see here, the first button is copy. That means if you want to copy this thing, you can copy it. If you want to move this, move means now this is in the center. So I can move it here somewhere like this. So you can use this add a line, which is basically a wire. So we can just pull it down here. Now this is named as I in 1. So if you double click on that button, you can see the name I in 1. Rename it to A. Rename it to A. Now you can select the colors that you want. If you want it to be red, then you can keep it red. Red means if you just simulate this thing, you can see when you press it, this becomes red. Okay, if you double click on this again and if you select yellow and then again run it, you can see that this button will become yellow. So it's up to you what color you like. So you keep the color that you like. I'll keep the standard one, that is red, and that is it. Okay. Now I want to make A bar. I want to make A bar. So I'll take an inverter. Again, I'll just rotate it and I'll put it here, and then with the help of a line, I'll just join this and I'll just pull a line down here. So yes, anybody has a doubt? So if you are facing any doubt, problems in actually working with DSCH and the options, please unmute and ask. I will explain. So has everybody understood how to create A bar? If yes, then type yes in the chat box. Now the same thing can be done in Logisim also. But Logisim will not give you a simulation, a time result. And it doesn't give you a Verilog file also. But in certain analysis, it is very good. So we will have a hierarchical approach. So this word also you will see when we go to Verilog. So what we are doing is a hierarchical design. Okay, so is everybody with me on the same page? Yeah. Now we want like this 4 of them, A, B, C, and D. So what you can do is you can just use this copy button and mark this entire thing. So you can you see what happened? I just copied the circuit, but then this A also got copied. So you need to rename A, make it as B. Now this entire thing I'll again copy and generate C and D. And generate C and D. So that is C, and here we have, you can see, and a D. If by chance something like this happens, like this goes down and all, here there is one button called as all. Here there is a button called as all. If you press all, whatever components you have put, you will see all of them. So the screen will resize itself to show you all the components. So sometimes if you are using it and if you are using these arrows, and if you want to come here and somehow you are not able to come exactly, just press all, you will see all the circuits. So try using the button all. Try using the button all. Okay. Now let us look at our functions. Let us look at our functions. The first function is B4. The first function is B4 equal to AB plus AC. The first function is B4 is equal to AB plus AC. AB means that's one product term and AC means another product term. So you will require two AND gates. You will require two AND gates and one OR gate. You will require two AND gates and one OR gate. So for the first AND gate, my terms are A and B. So I will just join this A and B. And for the second AND gate, it is AC. So here we will get A, and here I will join C. So this first AND gate will give me an output of AB. The second AND gate will give me an output of AC. And these two outputs I have to OR. So I will just join these two. By chance something like this happens, if you get an extension like this, then there is a gun here. If you want to delete something, there is a gun here. So you can just click on that, it will go. And finally, I want my output, I want to see the output. So I will take one LED and connect this here. And you can double click on that LED and you can just write here B4. This is my B4. So if everybody has made this, just write B4. Just write B4 in the chat box. If you have made this much, write B4 in the chat box. So like this, we have to fit 4 more functions. So obviously we will require some space. So let's create some space by taking this thing at the top. And now we will have to just extend these things. Okay. So my next term is B3, and which is simply A, B bar and C bar. A, B bar and C bar. So one 3-input AND gate will do. So A bar, A, B bar and C bar. So I will connect one to A, then other I'll connect it to B bar, and then the third I will connect it to C bar. So one line is A, the line besides A is A bar. Then we have B, the line besides B is B bar. Then we have C, the line besides C is C bar. Then we have D, the line besides D is D bar. Okay, and here also I will have a output. So the output here will be B3. Double click on it and just rename it to B3. Okay, the next is A bar B plus BC. A bar B plus BC. B2 is A bar B plus BC. So just see to it that you are placing the gates nicely. Everything should look aesthetically also good. So A bar B, A bar and B, and then we have BC. So here we go to B and here we go to C, and then everything has to be odd. Yeah. So this is my B2. Okay, and can you do B1 and B0 also? So B1 has got a 3-input AND gate and a 2-input AND gate. So we have a 3-input AND gate and a 2-input AND gate, and that's it. So 3-input is A, B, C bar. A, then we have B, and then we have C bar, and then we have A bar C, A bar and C. Okay, and then B not. So here you have to put the OR, and you put here two LEDs. Okay, so this is B, I think it's B1, and finally here we have B0, and you can just press all in a while, all, so you can see all. So you should be able to see this kind of a circuit. And most important, don't forget to save it. by default it gets saved in a file called as example.schematic, example.sch. Okay, so if you all have reached this place, now I want you to like look at the screen. Just look at the screen. Now you can press on simulate button and check. Now you can press on simulate button and check. So I want you all now to go to the truth table. I want you all now to go to the truth table. So the truth table you can see, let us put a valid input. Let us put 0, 1, 1, 1. So 0, 1, 1 should give me an output. You can see B4 should be 0, B3 should be 0, and B2, B1, B0 should be 1, 1, 1. And that is exactly what we are getting. That is exactly what we are getting. Now let's try an invalid input. So 10 is an invalid BCD number. So let's try 10, 1, 0, 1, 0. You can see B4 is 1. B4 is 1 because we wanted it to be that way. And B3, B2, B1, B0 is 0, 0, 0. You can try some more. You can try maybe 12. Is 12 an invalid number? Yes, it is invalid. So B4 is 1. And you can see B1 according to truth table is also 1. So we designed the circuit from the truth table. We designed the circuit from the truth table. Now whatever inputs we pressed just now, if you want to see that in waveform form, if you want to see that in the waveform form, then you can go to timing diagram and you can see here that the waveform has got automatically generated for the inputs that we have pressed. For the inputs that we have pressed. So this is what actually happens. So you can check here what is A, B, C, D. So accordingly, you can see this is 1, this is 0 here, this is 1 and again 0. That is why B0, B1, B2, B3 are 0 and B4 is 1, which indicates that this is a invalid BCD number. So 10 is a invalid BCD number. So if you have got this till this point, then you write done in the chat box. If you have got till this point, write done in the chat box. And if you are not done and if you are facing a doubt in some dragging, dropping, some renaming, some misalignments, some you want to delete, please unmute me and ask.
Hello, sir.
Yes, sure.
Sir, renaming का बताओ ना please फिर से.
Renaming the outputs and inputs.
Yes, sir.
Yeah, so just double click on the LED. This menu will open. Can you see here?
Yes, sir.
And it is asking you for the name. So you can put, what is your name?
Prathamesh, sir.
So we can write here Prathamesh also. In the Verilog code, Prathamesh will be one output. So Prathamesh will be 1 in case of invalid binary. So let's check. 1101 is, so you can see that Prathamesh is 1 and we have designed B1 and B0 to be 1. So that is why it is giving me 1 1 according to truth table. I'm just rechanging it to B4. Have you got it, Prathamesh?
Yes, sir. Thank you.
Yes. Anything, anybody? Yes, I want. Now instead of setting three inputs, instead of setting these three inputs, so I'm just saving this somewhere. Save as binary underscore 2 underscore bcd underscore lab. I'm just saying this is the name of the schematic. So I'm just saving it as again save as underscore 1. So just see now what I'm doing. Just see what I'm doing. I'm removing this input A, B, C, D. I removed it. And I'm taking this keypad. I'm taking this keypad. So you can see this keypad, and if you want to like test it, what this thing is, then you can use a 7-segment display to just check what this keypad actually does. So this is a keypad just, and you can see 0, 1, 2, 3, 4. So this is 0 should go here. So you can just connect it like this. This is A. This is B. This is C. And this is your D. Now if you simulate this thing, you can see if I press 1, I'll get 1, 2, 3, 4. Okay, so there is a slight mistake that I did. No worries. So I connected the reverse way round. So there was a slight mistake. So this is the LSB, and D is also our LSB. So LSB should come to LSB. This is the next LSB. And purposely I want to show this because if this overlap happens, no problem. But look, when you can see those green dots, that means there is a connection. So whenever there is no green dot, there is no connection. So now if I simulate this, you should see that 3 means you should see 3, all zeros and these two ones. Now till 9 you should see 1001. You can just remove this unnecessary thing. And if you want to see the 8 segment display, then fine, you can see that also. Just to so I hope you are getting the hang of it. So this is my MSB going to MSB. This is my LSB going to LSB. So let's check. So if I press a 1, I'll get a 1, 2, 3. You can see here till 4. If I press a 4, I get a 4 here. If I press a 5, I get a 5. If I press a 6, I get 6. But the moment I press A is 10, I get 0. The moment I press B, I get this thing. And this also very well you can check just by putting LEDs at different places. So you can put your LEDs here, which is basically your A, B, C, and D. So I'm using just LEDs for tracking the outputs. So this is A, B, C, and D. This is A. This is my B, and this is my. So sorry, this is C, and this is D. So instead of those keypads, instead of those buttons, now I'm using a keypad. Why? Just like that. I want to use. I want to use and check and see. So now if you simulate this thing, you should be able to see that if I press 7, I get a 7. The code for 7 is 7 only. For A it is 0. For B also 0, 1, C, D, E, and F. And my B4 bit is now 1. So that's what we get. So I hope you have understood this thing. If yes, then type yes in the chat box. So this was the first part of your experiment. Now there are many such things that we have to do. Here today in this lab, now let us say that if somebody tells you that I want to use this again, so I can't build this such a big thing again. I can't build this. I want this to be as a black box. So I'm just saving this and I'm opening my previous file. I'm just opening this binary to BCD underscore lab. So this was my previous file with the buttons. So with the buttons, it is slightly easy to imagine. Now you can see we have 4 inputs, A, B, C, D, and 5 outputs, B4, B3, B2, B1, B0. So what DSCH tells you is, let's check the Verilog file of this. Make Verilog file. So you can see the Verilog file is created. I say OK to it. BCD binary to BCD underscore lab.bs. dot schematic. Now I go to, now I am going to micro and now I'm going to micro and just micro and then say compile Verilog file, compile that is binary to bcd underscore lab, and the file has been read, and I say compile. Okay, back to editor. So I can see my outputs, that is B0, B2, B1 and so on, and then I can see ABCD. So these are my, this is the IC that we have actually made, and you can say analyze using the model. You can say DSIM 4, which is the latest model of the MOSFETs. And you can do the simulation. Just say stop. So this is what we can do. Now, all of you, can some of you share me your screen so that I can check whether what you are doing is right or not? Who, yes, Karthik or Anushka, can you share your screen? Divya, can you share your screen? Soham? Pranjali, have you completed it? You can unmute and talk. Okay, so I will take some names and they have to share their screen with me. Okay, Pragati Mali, can you share your screen? Pragati, is Pragati there? Okay, yes. Bhuvan, are you sharing the screen? Karthik, can you hear me? Krishna Prasad? Krishna Prasad, can you unmute and talk? Krishna Prasad Menon. Okay, Pragati, what happened? Okay, no one.
So I have performed. Can I show my screen? Hello. Is sir rejoining?
Yeah, was I not there for some time?
Yes, sir.
Okay, so Vishwas, have you completed it?
No, sir. Doing it now.
Okay, should I share my screen with everybody?
Sorry, sir.
I'm sharing my screen now.
Yes, sir.
So once you finish the circuit, just take a print screen of it and put it in the chat box. I would like to check the circuits that you are doing. Okay, Pragati is in her village. Okay, Shubham is the first one to give the answer. Okay, great. Okay, so this is a huge circuit. Very good. Now, one more thing I would like to tell you all. Let us make this as a black box. Let us make this as a black box. So you can go to file. You can go to file. And for this entire circuit, you can make one schematic. You can make your own schematic. So I am saying schema to a new symbol. So by default, you can see the Verilog is showing you. So you can make this thin or you can make this schema bigger. You can also reposition the inputs. That means from the top it is 1, 2, 3, 4. So if A is your MSB, you can make it, you can type here position 1, 2, 3, and this is 3. Let's say A1, 2, this is 3, and B is 4, and say refresh. It will give you ABCD. And on the other side, you can see B4, B3, B2, B1. Now, you can also see side here, left and right. So here you can type up and down also. So if you say up U, if you type here U, that A will go at the top. If you type here D, that A will come at the bottom. So where you want this pin, that also you can specify. So this is, I'm just saying it left to the left right now. Okay. And so this is going to be your so symbol property. So you can rename this file. You can give the title as the same thing. You can give the title as binary to BCD converter. So if you just say refresh, you can see here the name initially was 1. Now it became binary to BCD converter, and it is getting saved in this very folder with the name as, so instead of lab I will write symbol, name of the will be symbol, binary to BCD symbol converter, binary to BCD underscore symbol converter, and then say OK, and then say OK. Now if you want to see the circuit description of this, then it is inside this Verilog file. So how the inputs are connected to the outputs are described in this Verilog file. So inputs are ABCD, outputs are B3, B4, B2, B1, and Verilog file describes these connections. Verilog files will describe these connections. So that is how it is. Verilog is very simple that way. So I say OK. I can again go to iOS and say OK. So I'm saying OK. Now if you want to get back that file, you can say here open, or you can say insert, use user symbol. You can say insert user symbol. So just now we created this symbol, binary to BCD underscore converter symbol dot sym. So the file gets saved as dot sym, and I say OK. Now this entire circuit is now represented by this one small black box. So I can still have these 4 inputs A, B, C, D. Or instead of these buttons, now directly I can have a keypad itself. So directly I'm connecting that keypad only to this ABCD, and here I should be able to see the output, and this LED I will connect it on this pin. So just for simplicity and to reduce the clumsiness inside this, and so just now what we made is a chip. We made a chip of binary to BCD converter. So as electronics engineers, you should know chip design, and we not only made that chip, but we also simulated the performance. So you can see the picture posted by Shubham Dalvi. That is the picture of the chip. And Shubham, can you also post the simulation, please, till I complete this thing?
Sure, sir.
Okay. So if you just now say run, if this is the, can you see here, if I give 1 0 1 0, 1 0 1 0 is 10, that is A is 10. So all my outputs are 0. So that's my, all my outputs are 0 0 0, and my B4 is 1. So B4 is 1. So you get the same thing, but this time, if somebody tells me to just give me your designed BCD binary to BCD converter, I started from truth table. I made the logic functions. I implemented it using logic gates, and then I made it compact into just one small IC. So that's how the IC design happens. And this approach is called as a hierarchical approach. It is called as a hierarchical approach. So we have a black box, and it also works the same way this circuit works. So this is nothing but 101, that is 11. So the moment I click this, again we get this. So this is 7. Okay. So any doubts in this? Any doubts in generation of these symbols? Please ask. You can rename this also. The generic name is KBD, that is keyboard, but you can give a user title, that is keypad, and change that. Yeah. So even Yash has completed it. Yes. Good. Now, next. Now you have understood the complete steps of binary to BCD converter. Now you will create binary to XS3 code converter. You will design binary to XS3 code converter. So I'm just starting my presentation. Shubham, can you see my screen? So this is
Yes,
what
sir.
we did first. So this is B4 AB plus AC. This is B3 A B bar C bar. This is B2 A bar B plus BC. This is B1 A B C bar plus AC bar. A bar C, sorry. And this is your B0 straight away. So this is your logic diagram. This is what you get as your logic diagram. Finally, and you can see here that this line is connected to A, then the second line is connected to B, and the second term is AC. So it is one is connected to A, the other one is connected to C. So like this we do for all the functions. And we have we have not just implemented the logic diagram. So in the exam you have to do only till the logic diagram. In the exam you have to do only till this point. But in the lab we have gone one step ahead. We have made an IC, we have simulated the IC, and we have made a chip out of it. So that's how. So when you in our lab, in lab M201, whenever you come, we have Cadence software. We have software Cadence, and in Cadence you can read the Verilog file, and in Cadence you can read the Verilog file. So you can, whatever schematic you have created here, you can export it in Cadence. Then you can do some more operations like layout versus schematic. So that procedure is called as LVS. That procedure is called as LVS. What you did just now is you did the schematic. So you can see Shubham has posted first schematic, and the second one is called as layout. So whether layout and schematic gives the same result or not, that is also important. So actual simulation is one thing, and actually the output after making this circuit is another thing. So that is called as LVS, layout versus schematic. And once your LVS is perfect, you can go for something called as power supply planning or power plan or floor plan and so on. So though these are all advanced IC design terminologies, uh, for which what we are doing just now is a prerequisite, and that is why this lab is very important. So your next task would be this. Your next task would be this. Come on, write it down. Binary to excess 3 converter. Binary to excess 3 converter. So design and implement. Design and implement. Now your inputs are again ABCD, but this time your outputs are E4, E3, E2, E1 and E0. E3, E2, E1 and E0. You can see here that you can see these terms, that is from 0 to 12. So the excess 3 of 12 would be 15, that is 1111. But the excess 3 of 13 would be 16, that is 10000. So that is why we require this extra bit E4 just to indicate that we have crossed our limit of maximum number of bits, that is 4. And for 13, 14 and 15, my E4 bit is 1, which indicates that those are invalid excess 3s. So E4 is equal to 0 for valid. This should be excess 3. It should be for valid excess 3. And this is also for invalid. So I have given you the table. Now you have to design the K map. So at least tell me what are the outputs for E4, E3, E2, E1 and E0. At least tell me what are the outputs for E3, E4, E3, E2, E1 and E0 in terms of A, B, C. Sir, how to rename the components? Spark, you have to double click on that particular component. Now, what are you trying to rename? Are you trying to rename input or output?
Input, sir, input.
Yeah, so click on the buttons.
Yes, sir, I did it. I can do it now.
Okay. Okay. So binary to excess 3. Write the truth table and design. In exactly 10 minutes, you should design this. We have 10 minutes, and in exactly 10 minutes, you should design all 5 of them using Kmap and implement it on the editor. If you are done with E4, then write the answer of E4 in the chat box. If you are done with E4, then write the answer of E4 in the chat box. Excess 3 of 0 is 3. That is why you can see E3, E2, E1, E0 as 0011, which is 3. Excess 3 of 1 is 4. Excess 3 of 2 is 6, and so on. Sorry, 2 is 5. In the meantime, if you are solving, I am here to take some doubts. So XS3 is not very straightforward. There will be some weird terms. So if you have copied this truth table, just write TT done. If you want to copy the truth table, it is like this. Again, there are 4 inputs A, B, C, D and 5 outputs E4, E3, E2, E1 and E0. So let's go ahead and see E4. So this is the truth table and you can see E4 is 1 only for the last 3 terms. E4 is 1 only for the last 3 terms, that is 13, 14 and 15. So that is why in the place of 13, 14 and 15, you are having ones. So you can see here 13, 14 and 15. So here you have 2 pairs. One, this is the first pair, and then this is the second pair. And 2 pairs will give me 2 terms with 3 variables each. So the first term is ABD and the second term is ABC. So E4 is going to be ABD plus ABC. ABD plus ABC. Now if we go to E3, E3 gives me, so for E3 from 5 to 12, that is from 0101 to 1100, all are ones. So that is what I did. 5 from 5, 6, then we have 7, 8, 9, 10, 11, 12, 13. Sorry, not 13. So 5, 6, 7, 8, 9, 10, 11, 12. So this is one quad, pair, pair, and pair. So 2 quads and 1 pairs. That will give me 4 terms. Quad will give me A B bar. This will give me A C bar D bar. A C bar D bar. This will give me A. This has to be, according to me, it has to be A bar B D. It has to be A bar B D. I have just interchanged that A B bar. A bar B D bar. And the next one should be A bar B C. Should be A bar B C. So many of these things I do in the nights. Sometimes the bars can go here and there. Okay, anyways, I have corrected. So for E3, this is the answer. This is the answer for E3. Check it. Then let's go to E2. So E2 gives me like this. So this is one pair, quad and quad. So two quads and one pair. This is D, C bar, D bar. That's right. Then we have B bar, D and B bar, C. So E2 is going to be B, C bar, D bar plus B bar, D plus B bar, C. So similarly, we have E1, just two quads. So C bar, D bar, CD, which is just a XOR gate actually, XNOR gate. And E naught is a octave, so it is purely D bar. So this is how you should get the circuit. This is the final implementation of the circuit. This is E4, E3, E2, E1, and E2. Here also I have to make that small change. So this is how you can design all the circuits, and just for your sake, I have already designed this for you. I'll just open it. It says by CD to XSP converter. Okay, so I have already designed it, and I think it's there for us. E4 is missing, so we can just shift it out, not a big thing. E4 is A bar, A, B bar, C bar, D plus A, B bar. Yes. How? E4 is not A, B bar, C bar, D. E4 is this. It's on the screen. Are you convinced with that? Yes. Okay. So I have shown you all the outputs, and that's the way to design it. And I think it's 4 o'clock. So let us conclude our lecture. Just let me take the attendance. Don't log out. I hope everybody is here inside and nobody has left. So I'm stopping my screen share.
So regarding I,
Yeah. What regarding I?
sir, the modules, portion and type of questions.
Yeah. Whatever we have done till now, whatever will be doing till tomorrow, that will be there in for I. Whatever will be doing till tomorrow in tomorrow's class, that will be there for the I.
Okay, sir. So will theory be asked? Sir,
Hello, sir.
Hello, sir.
Yes, tell me.
sir, will theory questions be asked like select the correct definition of two variable K map and four options are given. We have to select the correct definition like that.
Yeah, that way option can come that way, but so it will be something like gate level, not gate level, but slightly one level below that, because still you have not completed the entire course. So none of you is competent enough to handle that level. But yes, the training is towards that only. So that is why you may have to handle those questions. So all questions will be objective. There will not be any subjective question. That is what at least till now department has told us. But I am not very sure about what is going to happen.